In this video, I want to talk about vector spaces other than Rn. That is, vector spaces that are not just a finite list of real numbers, maybe written in vector form. I'm thinking of this video as a continuation on the 3 blue, 1 brown vectors video. So if you haven't watched that yet, I recommend watching it first. Otherwise, some of what I say won't make sense. In that video, he talks about how you can think of vectors in 3 main ways: as lists of numbers, as arrows, and as things that can be added together and multiplied by numbers. And he deals a lot with the first two and draws some nice pictures in 2 dimensions and 3 dimensions, but doesn't really dive at all into that third way of thinking about vectors as things that can be added or multiplied by scalars. And that's what I want to talk about in this video. So let's start with an example. I have it written up here. And this notation isn't, I don't think, that standard, but we'll use this as an example a lot in this class, these polynomial vector spaces, because they're a nice example that isn't quite Rn, but also isn't too foreign. There's nothing totally crazy going on. So P2 will denote the set of polynomials of degree 2 or less. So they could have degree 1. They could just be constant. And another way of writing this, this is a bit notation heavy, this reads the set of ax squared plus bx plus c such that a, b, and c are elements of the real numbers. And this symbol here, this kind of e or epsilon looking thing, means is an element of. We'll see it a bunch in this course. As we'll see, it's nice shorthand. Anytime you have mathematical notation, it should serve a purpose. This doesn't just exist to be confusing. It exists because it's useful shorthand. Okay, so this is an example of a vector space that's not Rn. So why is this a vector space? Well, we have addition. And I'm going to do all of these just by example, but if I take some polynomial of degree less than or equal to 2, and I add some other polynomial of degree less than or equal to 2, I end up getting a third polynomial of degree less than or equal to 2. I also have scalar multiplication. Now this is scalar multiplication. I'm not talking about multiplying 2 polynomials by each other. So for instance, I could take -5 and multiply it by 2x squared plus 3x plus 1, and I would get another polynomial of degree less than or equal to 2. And then finally, I have 0. The 0 polynomial is just 0, but the whole point is that if I add this to anything, let's put parentheses around there to really indicate that we're multiplying or adding these elements, I just get the thing that I started with, right? So 0 has the property that when I add it to something, nothing changes. And so this ends up forming a vector space. And so far, I haven't quite justified that. That is, it's not really just enough to have addition, multiplication, and 0. Really, you need a lot more. And this is a bit overwhelming. I'm going to page 84 of the textbook. This is the definition of a vector space over the real numbers. And I want to just say we're not going to use this definition all that often. What this definition is saying is that we have addition, we have scalar multiplication, and we have 0, and these things have certain properties. So properties 1 and 6 are just the closure properties. They're saying that when we add 2 things, we get a third thing in the set. So when we add 2 polynomials of degree less than or equal to 2, we get a third polynomial of degree less than or equal to 2. 6 is saying it's closed under scalar multiplication when we take a polynomial of degree less than or equal to 2 and multiply it by a real number, our resulting polynomial is less than or equal to 2. Then we have a lot of properties about commutativity, associativity, and distribution. So property 2 says that vector addition is commutative and associative. That's property 3. Property 9 says that scalar multiplication is associative. Properties 7 and 8 say that Scalar multiplication is distributive in certain ways. And then finally, we have some properties related to 0, property 4 and 5, saying that when we add something to 0, we get the same thing. And we have a property related to multiplication by 1. That's property 10. Okay, so what I just said might not have really clicked, and that's fine. The point is that if you go through all of these properties, these are properties of the real numbers that you kind of just take for granted. And if you're working with Rn, like R3 or something, you might just do something like switch the order of addition of two vectors and never think about it. But when we get into other types of vector spaces, we do have to be careful because we shouldn't just assume that something's true. So anyway, these are the properties that define something being a vector space, and you can confirm on your own, it's not too hard to show, that the set of polynomials of degree 2 or less satisfies all of these properties. So this is what's known as a vector space over R. Let's go to another example of a vector space over R. The set of continuous functions from R to R. And we can write this in kind of shorthand. Set of, this means a function whose domain is the real numbers and whose codomain is the real numbers, or whose range is the real numbers, depending on the terminology you want to use, such that f is continuous. So just all continuous functions from R to R. This forms a vector space. We can add two functions. And I'm doing these again by examples, but if we have, for instance, the function f of x equals sine x, and we have the function g of x equals x squared minus 7, then f plus g of x is sine x plus x squared minus 7. We also have scalar multiplication. Again, this is scalar multiplication, right? We're not multiplying functions by each other, but if I again use my example of f of x is sine x, then 3f of x is just 3 sine x, and we have 0. What's the 0 function? Well, the 0 function is just the function defined by h of x equals 0. And with this addition that I've defined by example, but hopefully you see what's going on, and this scalar multiplication and this 0 function, we actually get something that satisfies all 10 of those properties that I'm not going to pull back up onto the screen. Okay, so we have this notion of a vector space that's not Rn. And you can look through those examples or those properties, the list of vector space axioms. You can look at these examples and hopefully convince yourself that this works. But there's a question you should always ask. It's not just you aren't just being kind of contrarian or anything to ask this, but which is why? Like, why do this? Like, why are we talking about this? Why do we have to go away from Rn and talk about how other sets have the same sort of properties as Rn? And to justify why we're doing this, I want to go back to P2, because I think this is going to be the place that where we can see most why this is useful. When you look at this second way of writing P2, you might start to notice that, well, these polynomials are dependent on these constants, and there's 3 of them, and they're all from R, and this is really starting to look like R3 to me. And I can formalize that, or, I mean, I guess make more formal. I don't want to overdo it. But if I take something in P2, so if I take like 3x squared minus x plus 3, it feels like this is kind of just, this was a bad example. Let's change it. Make this 2. I want to make clear where the numbers are going, because there are choices. There's no reason you should put them in this order. I kind of want to say, look, let's go back and forth like this, right? This 3 is just my first entry of a vector. This -1 is just my second entry. and this 2 is just my third entry. I really kind of want to say, yeah, this is really just like R3. And it works really nicely, actually, because then you start to do things. You start to add vectors over here. Here, what we're adding are polynomials. And then you add the corresponding ones in R3. Right, so x squared plus x minus 2 is 1, 1 minus 2. X plus 3 is 0, 1, 3. And when I add these vectors in R3, I get 1, 2, 1. And what we notice is that addition respects this relationship, or stated better, this relationship respects addition. Right? When I translate these polynomials into vectors in R3 and then add them on both sides, I get the same thing. And the same is true of scalar multiplication, right? So if I were to take 3 times x squared plus x minus 2, I would get 3x squared plus 3x minus 6. And at the same time, if I write this x squared plus x minus 2 as a vector in R3 and multiply it by 3, I get this same thing, 3, 3 minus 6, which is the vector representation of this polynomial. And then finally, we shouldn't skip this. If I have 0 over here in P3, that's really 0x squared plus 0x plus 0. Under this correspondence that I've defined, this thing corresponds to the 0 vector in R3. And so what this means is that thinking of P2 as a vector space with addition, everything that happens in R3 is going to be the same in P2 under this relationship. And in particular, anything we learn about R3 as a vector space will be true of P2 as a vector space. We'll eventually start talking about linear transformations of vector spaces. And what we talk about for R3 will naturally translate to P2. We'll talk about eigenvalues, determinants, all of that stuff, even if you don't know what it means now, once you understand what happens in R3, because the addition and scalar multiplication in P2 follow the same properties, everything we learn in R3 we can translate to P2. And this is really powerful. This means that we don't have to reinvent the wheel when we're trying to study polynomials. Okay, so maybe, hopefully I've convinced you that this is something worth thinking about, right? A bit of an answer to the why question. But you can almost go to the other extreme then and you say, okay, you've convinced me that it's worth thinking of P2 as being R3. But you can overdo it, right? And say, okay, but you've overconvinced me, and now I've decided, look, we still don't need to think of P2 as a vector space. Let's just translate everything into R3, right? If I give you this polynomial, you're going to say, oh yeah, it's just this thing. You don't want to do that either, because as it turns out, P2 has a lot more going on than R3 does, right? So for instance, and I've run out of space here, but we can just scroll down. So in P2, it makes sense to do things like take a derivative. That's a totally reasonable thing to do, right? If I write this statement, this makes perfect sense. Can we take a derivative in R3? Right, so if we're viewing this in R3, now all of a sudden we're taking this vector over here and we're doing something to it, and it turns it into this vector. Does that really make sense? So we don't want to throw away all the structure of P2, right? We don't want to just pretend it's R3 because there's other stuff going on in the background. But as it turns out, the derivative is a linear transformation. And so this sort of statement, you might have thought, like, why are we talking calculus? But I would argue that when we start talking about derivatives, it's calculus, but it's also linear algebra. It's very much in the realm of what we're doing in this course. So P2 has this additional structure that we don't really want to think about. But on the converse, R3 also has additional structure, right? So if I'm studying these two vectors, or sorry, these, I'm calling them vectors because it's a vector space. That's not incorrect, but these two polynomials, if I'm looking at the two polynomials in P2 given by, I want to make sure I have my examples lined up, 3x squared minus 2x plus 3. If I'm looking at this polynomial, and then I'm also looking at this other polynomial, let's call this P of x, and let's call this one Q of x. And that's going to be x squared plus 3x plus 1. And I just decide that I'm thinking of them in terms of R3, you can do something that also doesn't make sense, which is to say, hey, well, if I'm thinking of these vectors, let's draw them as arrows. And so here I've drawn these two vectors as arrows. So this is the blue vector here, and then the red vector is Q of x. Right, I've drawn these as arrows when I represented them in R3. And I'm going to look at these here. Hopefully you can realize that this might not make sense, right? So for instance, if I look at these two vectors, it looks like P of x is longer than Q of x. But does it make sense to say that one polynomial is longer than another? And similarly, if you put this at the correct angle, you can see that these are perpendicular. There's a right angle between them. But should we really say that these two polynomials are perpendicular to each other? We shouldn't just take terms and apply them to things that we don't really know what they mean. So R3 also has additional structure that we'll talk about in this course that we don't want to think about as applying to polynomials. And so this is another important perspective. It's not just that we're studying vector spaces that have more structure than R3 that's not related to being a vector space. R3 also has structure that isn't really directly related to it being a vector space. And so all of this to be said, that this is going to be incredibly useful for us to be able to think of this vector space P2 and think of it as something that in some senses is the same as R3, but in other senses is not. And so that's really what we mean when we talk about these other vector spaces. I want to quickly revisit these continuous functions again, because as you start to think about continuous functions, you realize that I gave you just two examples of continuous functions. It's not going to be quite so easy to associate this with Rn for some n. And in fact, you can't, right? There's not some finite number of constants that you can associate with continuous functions and always be able to write every continuous function in terms of them. And so the continuous functions is a different type of vector space. It's what's known as an infinite dimensional vector space that can't actually be directly represented as Rn for any n. And that's another justification for why thinking of vector spaces in this abstract manner as things where we add things and multiply things is a useful way to think about it. Because we can't just study Rn. We can't just study the continuous functions from the real numbers to the real numbers by taking some Rn for some n and studying that. But even better, I mean, that motivates why we need to do it. But it turns out that a lot of what you do for Rn does actually apply to these infinite dimensional vector spaces. In this course, our main focus will be on Rn, and our secondary focus will be on things like P2, what are known as finite dimensional vector spaces. These are vector spaces that aren't Rn, but are in some sense the same as Rn for some value of n. Right here, P2 is really, as a vector space, the same as R3. Occasionally, we'll mention things, these infinite dimensional vector spaces, like the space of continuous functions from R to R, but that won't be our main focus. Our main focus will be on finite dimensional vector spaces.